Okay, hi everyone. I'm Andreas, a cryptography researcher at Brainboard working on the Shutter network. And I'm going to talk about a novel anti-collusion mechanism for threshold encrypted mempools. This is a topic that I also wrote an ETH research post some time ago about, so if you're interested, feel free to scan that QR code. I'm also going to show the QR code later on again, so in case you don't make it now. Okay, I would like to start off by recalling what we refer to when we say the term MEV. So let's say we have a user in Ethereum that wants to make a trade. For example, the user wants to buy ETH and sell Smiley coin. Then the user sends that transaction to the public mempool. Eventually, a proposer picks up the transaction, includes it into the block, and when the block is included into the blockchain, the transaction is being executed, and yeah, the trade is being executed. The impact of this trade is that the price of ETH is going up and the price of Smiley coin is going down. Now, of course, the proposer knows about this price movement, and what a malicious proposer could do is it could just include a transaction right in front of the user transaction, which is called the so-called front running. And what this does is the proposer essentially buys a token knowing that the price of this token is about to go up. And for the user, the impact is that the user buys this token at a higher price. To make this even worse, the proposer could do a sandwich attack where it also includes a transaction right after the user transaction. And essentially for the user, this means that it buys the token at a high price, and right after the user buys the token, the price is falling. And the value that is being extracted in this manner is called MEV, and actually a recent report by the European Securities and Markets Authority estimated that the total amount of MEV stolen in Ethereum in this way ranges somewhere between 1.1 and 3 billion US dollars. So this is obviously a pretty big problem that we need to tackle. And one promising idea to do this is to use encrypted mempools. In encrypted mempools, the user sends its transaction in encrypted form so that no one in the network can actually see the content of the transaction. And only when the proposer includes this encrypted transaction at the top of the block, the decryption key for the transaction is being released, the transaction can be decrypted and executed. Now, this is a nice design, but there are two big problems that we need to think about. First of all, where does this decryption key come from? And second of all, what actually forces a proposer to include this transaction at the top of the block? So for the first question, where does this decryption key come from? Typically, we have something that is called an encrypted mempool service provider that provides the network with the necessary keys. So the service provider first provides a public encryption key to the network that users can use to encrypt their transactions. And when this transaction is included at the top of the block, the service provider releases the corresponding decryption secret key. Second question, what forces the proposer to actually include the transaction at the top of the block? And there are several different ways to go about it, but one interesting idea is to use proposer commitments. Proposer commitments essentially allow a proposer to make a commitment about the allocation of the space in the block that the proposer is about to propose. And the best known example for proposer commitments are pre-confirmations where the proposer can promise to a user that it is going to include a user's transaction, but it can actually be also used to build out-of-protocol encrypted mempools. Actually, we wrote some month ago another ETH research post about this, so if you're interested, again, scan the QR code. So how does this look now? Like how can we build an encrypted mempool using proposer commitments? We have the user that sends an encrypted transaction to the mempool. The proposer picks up this encrypted transaction and sends a public commitment which says, I commit to including the decryption of this encrypted transaction at the top of my block. And when the service provider sees this commitment, it releases the decryption key because it knows the proposer is now committed to actually include the transaction at the top of the block. The nice thing about this is exactly this accountability. We know that we can hold the proposer accountable if it does not act upon its commitment. And just as a technical detail, because this will become important later on, The proposer commitment is essentially a BLS signature issued by the proposer. Okay, so this is a nice design, but there's quite some significant power accumulated in the service provider, because essentially the service provider decides when a transaction is being decrypted. So it makes sense to think a little bit about how do we actually want to instantiate the service provider. And there are different ways to go about it. One idea is we can just say it's a trusted party. The other idea is we say we use some secure hardware like a trusted execution environment. And then there are cryptographic approaches like using delay encryption and threshold encryption. All of these approaches unfortunately have their drawbacks. Trusted party is kind of self-explanatory. TEs rely heavily on hardware assumptions. Delay encryption has timing issues and also relies on hardware assumptions. And threshold encryption relies on the so-called threshold trust assumption. And in this talk, I'm going to focus on the last one, on threshold encryption. So just to recap, what is threshold encryption actually? Essentially, it is a public key encryption scheme with a decentralized decryption mechanism. So basically, it proceeds in 3 phases. We have an initial one-time distributed key generation, where a set of parties that we also call keepers initially generate a public encryption key and a sharing of the corresponding decryption key. In the second phase, a user can use this public encryption key to encrypt a message locally, and this encrypted message can be decrypted again by the keepers collaborating. We have typically several properties for such a threshold encryption scheme. The first one is kind of correctness, which says if a certain threshold of keepers collaborate, so for example, I denote the threshold here by T, then this threshold of keepers can decrypt the message. So for example, in the previous slide, I had 5 keepers. We could set the threshold to 3. That means that any set of 3 keepers can decrypt messages. And for security, we usually say that any set of keepers below this threshold does not learn any information from a ciphertext about the plaintext. And compared to a centralized solution, this is basically just distributing the trust among the set of keepers. Okay, so how does now, at a high level, look a threshold encrypted mempool? So we have the user that sends an encrypted transaction to the mempool. Eventually, a proposer picks up this encrypted transaction and sends a commitment for this encrypted transaction to the keepers. When the keepers see the commitment, they decrypt the transaction and send it back to the proposer for inclusion in the block. So it seems like a nice design, but there's a problem that I mentioned earlier, namely the threshold trust assumption. This is the assumption that maximum T-1 keepers act maliciously. Why do we have to assume this? This is because if we have more than T or more keepers that act maliciously, they could just collude and decrypt transactions prematurely and try to front run them. And actually, this is a problem that several academic works have looked at in the last 1 or 2 years. And these academic works have done good progress to kind of reduce this threshold trust assumption, but there's not really any practically feasible solution yet. However, these works, they have looked at the general case of using threshold encryption kind of for any use case. And in my talk, I'm kind of just interested in encrypted mempools. So the idea is, can we maybe find a way to reduce this assumption for the specific case of encrypted mempools? The good news is yes, and I would like to kind of first at a high level explain the idea or how to think about it. So if we think about it, what do we really want to prevent? We want to prevent that keepers can decrypt transactions before the proposer has actually committed to including the transaction. So we want to make it somehow technically infeasible for the keepers to do that. Maybe just to clarify again, the malicious MEV extraction can only happen before the proposer commits, because after the proposer commits, the keepers are actually supposed to decrypt. Or said differently, if the proposer does not commit, then the transaction stays encrypted no matter how many keepers act maliciously. Okay, now how can we achieve that? And I'm going to show this at the example of Shutter. Shutter is a commit and reveal scheme that uses threshold encryption. It has several use cases such as shielded on-chain voting, sealed bit RFPs, and especially encrypted mempools. And there's one property about Shutter that is particularly interesting, namely the decryption key in Shutter has the form of a BLS signature. And now that I say BLS signature, maybe you remember that I mentioned BLS signatures before, namely when talking about proposer commitments. So the main insight is really the following two observations. We have decryption keys in Shutter that are BLS signatures, and we have proposer commitments that are BLS signatures. So why don't we just combine these observations and we say we use a proposer commitment as a decryption key? So how would this now look like? How can we use this insight to build an anti-collusion mechanism? Let's say a user wants to send an encrypted transaction. So it encrypts the transaction first towards the keepers, and then it takes this encrypted transaction to encrypt it again towards the proposer. So we have essentially like a doubly encrypted transaction, and the user sends this doubly encrypted transaction to the mempool. The proposer picks up this doubly encrypted transaction and sends a proposer commitment for this doubly encrypted transaction to the keepers. And remember that the proposer commitment is a BLS signature that can be used as a decryption key. So what the keepers do now, they receive this doubly encrypted transaction and they receive a proposer commitment. So they use the proposer commitment to kind of take off the first layer of encryption, kind of to remove this doubly encrypted transaction and obtain the single encrypted transaction. And the single encrypted transaction, the keepers can now decrypt with their own secret key. And then they send back the plaintext transaction to the proposer. So why does this achieve exactly what we want? Essentially, we wanted to avoid that keepers, no matter how many of them are malicious, can decrypt transactions without the proposer commitment. And since the proposer commitment is necessary to kind of take off the first layer of encryption, without the proposer commitments, the keepers cannot do anything. So this is exactly what we wanted to have. I want to add a little bit of discussion. So one reason why I'm kind of excited about this is that it comes with essentially no overhead. At least if we talk about encrypted mempools using proposer commitments, the proposer anyway has to send a commitment. So we might as well just use it as a decryption key. The only little overhead that we have is that the ciphertext is a little bit larger. One might wonder, why do we actually need keepers if the proposer has the ability to use its commitment as a decryption key? So maybe we just use the proposer kind of alone for decrypting transactions, but we actually need the keepers to hold the proposer accountable. If we didn't have the keepers, then the proposer could just locally generate its commitment and locally decrypt transactions and front run them. And finally, one drawback of the current design is that the user has to encrypt currently a transaction for a specific proposer, which is of course not that great from a usability standpoint, but we can just let the user encrypt towards several proposers using something that is called multi-recipient encryption. And then the final point that I kind of want to make is that the main observation of this talk should really be that we can use BLS signatures as decryption keys, and this is actually not my observation. This was observed by several academic works before, but it can be very useful in Ethereum in general. So I showed here how we can use this for an encrypted mempool using proposer commitments and using threshold encryption, but we could also use this for encrypted mempools using other technology, such as trusted execution environments. And we could also use this for encrypted mempools that don't use proposer commitments, but for example, that use Fossil, which is an inclusionless design that also uses BLS signatures. And in general, BLS signatures are used kind of everywhere in Ethereum, so there might be other use cases, and every one of you is invited to think about use cases where we can use this observation. So yeah, just as a conclusion again, BLS signatures can be used as decryption keys. BLS signatures are widely used in Ethereum. I just showed kind of one use case of how we can use this for encrypted mempools via proposer commitments, but we can probably use this observation more widely in Ethereum. And with that, I'm through, and thank you for your attention.
Does anyone have any questions? Oh, I can see already, yep.
Thank you. I'm curious if you can comment on the concrete deployment settings, if you have any? Like how many nodes are we talking about in the threshold decryption consortium, and how are they incentivized to operate these nodes?
So this anti-collusion mechanism is not deployed yet. We do have, in Shutter, we do have a set of keepers that is running, that has currently, that it is running on Gnosis chain, and I believe we have 7 keepers, but I'm not exactly sure on the number right now. Yeah.
Is there any explosion in the overhead if you onboard, like, let's say 100 more?
No, this should be completely independent of the set of keepers, right? Because it's just kind of like this proposer commitment that is used as a decryption key. This should be completely independent of the set of the keepers.
Even the ciphertext size? Sorry for squatting the mic. Has anyone else said?
Yeah, so for the ciphertext size, that's a good point. So ideally, we want that the user encrypts transactions to several proposers, because the user cannot predict which proposer will actually include the transaction. And then, of course, the ciphertext, if you do it trivially, the ciphertext grows linearly. But you can use multi-recipient encryption, which kind of reduces the size of the ciphertext. Yeah.
Cool, thank you.
Any other questions? All right, let's have a round of applause.